Okay, let's do some problems on unconstrained optimization. So what's the algorithm? Compute gradient of f, equate it to 0, get the critical points, and at every critical point, check whether it's a local maximum, a minimum, a saddle point, or none of these. That's the procedure. Now, take an example. Say f of xy equal to x square minus y square. First, calculate del f. Del f is what? Dou f by dou x, dou f by dou y here. No? That is that dou f by dou x is 2x and dou f by dou y is minus 2y. So del f equal to 0 implies 2x equal to 0 and minus 2y equal to 0 implies x equal to 0, y equal to 0. So 0, 0 is the critical point here in this case. Now we need to check what is the nature of that critical point. Does that produce a maxima or minima or none? Let's see. Okay, so get that discriminant Hessian fxx, I mean second derivative f(x) of xy equal to what again? 2, and fxx at 0, 0 is again 2. Fyxy equal to minus 2 and fyy at 0, 0 equal to minus 2. And fxy at xy equal to 0 and fxy at 0, 0 is 0. We see that the discriminant is fxx into fyy minus fxy whole square. That is 2 into minus 2 minus 0 square. That equal to minus 4, which is less than 0. So since d is less than 0, here we are seeing, no? Here is the algorithm. If d is less than 0, then 0, 0 is a saddle point in this case, right? So that's neither maxima nor minimum. Take another example. F of xy equal to 8y cube plus 12x square minus 24xy. Let's find the gradient of f. So fx equal to 24x minus 24y and fy equal to 25y square minus 24x equal to 0. So fx equal to 0 implies x equal to y. Plug in that x equal to y in the second case. fy equal to 0 implies 24y square minus 24x actually, but x equal to y, 24y equal to 0, which implies 24 into y times y minus 1 equal to 0, which implies y equal to 0 or y equal to 1. Couple that with x equal to 0. So we get 0, 0 and 1, 1. These are the two saddle points. Now we need to inquire its nature. For that, we calculate the Hessian. Here it is. Critical point is 0, 0 is a critical point, and the discriminant here is Hessian is minus 576, so which is less than 0, so it's a saddle point. Let's see the nature of 1, 1. 1, 1. We know fxx equal 24, fyy equal to 48, and fxy equal minus 24. Discriminant d equal to fxx into fyy minus fxy whole square, that's 576. We see that d is greater than 0 and fx is greater than 0. So it's a local minimum. If it's the other way, no, d is greater than 0 and fxx less than 0, then what happens? Here it is. No? D is greater than 0 and fx is less than 0, then it's a local maximum. But here, in this case, D is greater than 0 and fxx is greater than 0, so it's a local minimum. Take another example. fxy equal to x cube plus y cube minus 3x minus 3y square plus 1. Calculate the gradient. What is fx? Fx equal to 3x square minus 3. Right? Fy, what is fy? 3y square minus 6y. Right. Fx equal to 0 implies 3x square minus 3 equal to 0, which implies x square equal to 1, which implies x equal to plus or minus 1. Fy, That's 3y square minus 6y equal to 0 implies 3 times y into y minus 2 equal to 0, which implies y equal to 0 or y equal to 2. So couple that with the earlier case, then we get the critical points as a minus 1, 0, 1, 0, and minus 1, 2, 1, 2. So there are 4 critical points here. Now we need to inquire which of them produces a local maxima or a minima, and we want to test the nature of each critical point. First take minus 1, 0. Here f equal to 3. We have seen fxx equal to minus 6, fyy equal to minus 6, fxy equal to 0. D equal to fxx, ffy minus fxy whole square. Plug in all these things here. No, you get 36. And we see that D is greater than 0 and fxx is a minus 6, which is less than 0. So it's a local maxima. Similarly, take 1, 0. We see that f at 1, 0 equal to minus 1, fxx at 1, 0 equal to 6, fyy at 1, 0 equal to minus 6, and fxy at 1, 0 equal to 0. And calculate the determinant fxx, fyy minus fxy whole square, right? That equal to minus 36. We see that d is less than 0 and fxx is greater than 0, right? So since d is less than 0, irrespective of fx, since d is less than 0, we see that 1, 0 is a saddle point. Similarly, take minus 1, 2. At minus 1, 2, we see that f equal to minus 1, fxx equal to minus 6, and fyy equal to 6, and fxy equal to 0. Plug into the d, fxx minus fyy minus fxy whole square. Plug into the d, we see that d is less than 0. So it's also a saddle point. Now take 1, 2. F at 1, 2 equal to minus 5, fxx at 1, 2 equal to 6, fyy at 1, 2 equal to 6, fxy at 1, 2 equal to 0. So we see that d, which is equal to fxx, fyy minus fxy whole square, we see that d equal to 36. We see that d is greater than 0 and fxx is greater than 0. So we can conclude that 1, 2 is a local minimum. So among these 4 points, the nature at these 4 critical points, minus 1, 0 is a local maxima, 1, 2 is a local minima, and the other 2 critical points, namely 1, 0 and minus 1, 2, they are saddle points. Okay. Let's take another example. fxy equal to xy into 1 minus x minus y. First, get the critical points. Here, f equal to xy into 1 minus x minus y. Go for the expansion, then it will be xy minus x square y minus xy square. Calculate the gradient here, fx. fx equal to y minus 2xy minus y square. Take out y as common, then it's y times 1 minus 2x minus y equated to 0. You get either y equal to 0 or 1 minus 2x minus y equal to 0. Now, fy, what is fy? Fy is x minus x square minus 2xy. Take out x common, so x times 1 minus x minus 2y equated to 0. This gives either x equal to 0 or 1 minus x minus 2y equal to 0. Now, simultaneously, you solve these two. Then you get the two solutions of fx equal to 0 and 2 of fy equal to 0 gives, yeah, obvious, there will be 4 combinations. We'll see one by one. Y equal to 0 and x equal to 0 gives one critical point, that is 0, 0. Y equal to 0 and 1 minus x minus 2y equal to 0. That gives xy equal to 1, 0. You plug in y equal to 0 here. You plug in y equal to 0. Then you get x equal to 1. Similarly, 1 minus 2x minus y equal to 0 and x equal to 0 gives plug in x equal to 0, which gives y equal to 1. Okay, so you get 0, 1 as a stationary point. So the first equation gives y minus x minus 2y. Plug in all these things and simultaneously you solve. So finally you get 1 by 3 and 1 by 3 is another stationary point. Okay. So finally we get 0, 0, 1, 0, 0, 1, 1 by 3 and 1 by 3. These are the four critical points. Now we need to inquire the nature. For that, we need the Hessian. What is the Hessian here? fxx minus fy, fxx into fyy minus fxy whole square. Let's take the critical point, first critical point, 0, 0. F at 0, 0 equal to 0, fxx at 0, 0 is 0, and fyy at 0, 0 is 0, and fxy at 0, 0 is a 1. What is the Hessian here? Fxx fy minus fxy whole square, that is equal to minus 1. So we see that d is less than 0. So 0, 0 is a saddle point. Now take another critical point here, 1, 0. F at 1, 0 is 0, fxx at 1, 0 is 0, fyy at 1, 0 is minus 2, and fxy at 1, 0 is minus 1. So d, again we see that fxx fyy minus fxy whole square, d plug in here, so we see that d is also minus 1. So d is also less than 0. It's a saddle point again here. Now 0, 1. F at 0, 1 is 0. Fxx at 0, 1 is minus 2. Fyy at 0, 1 is 0. Fxy at 0, 1 is a minus 1. And the discriminant is minus 1. So d is less than 0. It's a saddle point. So all these three are saddle points. Now let's see what is the nature of the critical point 1 by 3, 1 by 3. F at 1 by 3, 1 by 3 is 1 by 27. Fxx at 1 by 3, 1 by 3 is minus 2 by 3. And fyy at 1 by 3, 1 by 3 is a minus 2 by 3. And fxy at 1 by 3, 1 by 3 is a minus 1 by 3. So the discriminant is 1 by 3 here. Fxx minus fyy minus fxy whole square. Plug in 1 by 3, 1 by 3 here. You get a 1 by 3. Now we see that d is greater than 0 and fxx is less than 0. So this is a local maximum. Okay. So now we understand the procedure. Two-step process, simple process. First, equate the gradient to 0. Right? If it's a function of two variables, fx, dou f by dou x equal to 0, dou f by dou y equal to 0. If it's a function of many variables, then calculate the derivatives accordingly. For example, if your function f is a function of three variables, f of x, y, z, then gradient is dou f by dou x, dou f by dou y, dou f by dou z, the vector, equate it to 0, then you get dou f by dou x equal to 0, dou f by dou y equal to 0, dou f by dou z equal to 0. So all these three simultaneously, that will pop out the critical points. Right? Once you get the critical point, go for the Hessian, the second derivative test. Right? If a Hessian is positive definite, then what happens? If a Hessian is negative definite, what happens? All those things we have seen. Yes, you can extend the topic, the algorithm for n variables here, right? Okay. There is another example here. You can go through. Yeah, you just go through yourself. Fxy is x power 4 minus 32 x square plus y power 4 minus 18 y square. These are all the second derivatives. Plug into the Hessian. Then to get the stationary points, equate dou f by dou x to 0, dou f by dou y to 0, dou x by dou y. Dou f by dou x equal to 0 implies x equal to plus or minus 4, 0. Dou f by dou y equal to 0 implies y equal to plus or minus 3, 0. So the possible critical points are 0, 0, plus or minus 4, plus or minus 3, and plus or minus 4, 0, 0 plus or minus 3. So the four critical points we get is 4, 3, 0, 0, 4, 0, 0, 3. Calculate the second derivative at every stage. These are the second derivatives. For 0, 0, we see that the Hessian is negative. So, and fxx we have seen, the second derivative is greater than 0, right? Since d is less than 0 and fxx is greater than 0, we conclude that 0, 0 is a point of local minimum, right? We'll see next class. We'll see what is a constrained optimization. In a constrained optimization, objective function will be coupled with constraints. You have to solve the problem with constraints, right?